And last but not least, question 10. A rocket is travelling in a straight line with an initial velocity of 140 metres per second. It accelerates to a new velocity of 500 metres per second in 2 stages. During the first stage, its acceleration, a, after t seconds, is given by that function, 240 sine 2t, where 0 is less than or equal to t is less than or equal to k. And you're asked to find an expression for the velocity, v metres per second, of the rocket during the first stage. So we know, for part A, we know that A is equal to dv dt. Acceleration is change in velocity over change in time. And therefore, v is equal to the integral of A dt. So in this case, v is equal to the integral of 240 sine 2t dt, which you may well be able to do in your head, which is great if you can. If not, I'm going to take 240 outside of my integral. I'm going to perform the substitution. U is equal to 2t. So we get 240 sine u dt. But that's no good, so I need to transform my dt into a du. So du by dt is equal to 2. So therefore dt is equal to a half du. So this is 240 times the integral of sine u times a half du, which is 120. I can bring my half as a constant out of my integral. The integral of sine u du, which is minus 120 cosine u plus c, and then subbing my u back in, minus 120 cosine 2t plus c. I'm not done because I need to find my c, but it does tell me that my initial velocity is 140 metres per second. So when t is equal to 0, v is equal to 140. So I have 140 is equal to minus 120 times cosine 0, which is 1. So minus 120 plus c, so c is equal to 260. And therefore v is equal to minus 120 cosine 2t plus 260. So you're told that the first stage continues for k seconds until the velocity reaches 375 metres per second. You're asked to find the distance the rocket travels during the first stage. So I know, just get another sheet of paper, I know that s is the integral of v dt. But I do need to work out my limit. Now I know my initial limit is 0, but I need to find what k is. And because I know it reaches 375 metres per second, if I sub that into my previous equation, I have 375 is equal to minus 120 cosine 2t plus 260. I can find the value for t. Now I could do this a number of ways. I'm just going to do this actually algebraically, so I get minus 120 cosine 2t. Subtract 260 from both sides is equal to 115. So cosine 2t is equal to minus 115 over 120. 2t is equal to, I'm just going into my normal calculator mode, and I have inverse cosine of minus 115 over 120, which is 2.8519 seconds, and so my time is just that value divided by 2, 1.43 seconds. So I know that my value for s is the integral between 0 and 1.43 of my velocity. So that's minus 120 cosine 2t plus 260 with respect to time. Now I could do that analytically, but seeing as I have my GDC with me, I can just do that using my graph. I plot my function, minus 120 cosine 2x plus 260. I draw that function. I suspect my window is going to be unhelpful, so I go to Zoom, Auto. My window is more helpful there, certainly. And then I'm going to g-solve an integral, and I need to integrate between my lower 0 and my upper 1.43. And they shade that point to get that S is equal to 355 metres. Now, there will be some slight discrepancy on some calculators with that value. I know that you can get 354 metres using the Texas Instruments, for example. Part C. During the second stage, the rocket accelerates at a constant rate. The distance which the rocket travels during the second stage is the same as the distance it travels during the first stage. That's going to be important here. Find the total time taken for the two stages. There are lots of things I could do. One thing I'm going to do is write towards the bottom of my paper here, total time, so that I don't forget, because I need to work out the time it takes for the second stage. Now, I think the nicest way to do this is to think about a graph of your acceleration, or no, in fact, let's go velocity time, because it's the area under that graph that's really going to give you your distance travelled. And because we know the distances travelled are the same, that'll be useful. So initially my velocity follows this function we found in part A, but then I continue to accelerate at a constant rate, so that's a straight line. I know that my value of velocity here is 375 metres per second, and this took 1.43 seconds. What I need to find is this time here. That would be useful. But actually, to make my life easier, I'm going to call this length here 1.43 plus delta t. That will become apparent shortly. And I notice that this shape here is a trapezium. I know how to find the area of a trapezium. So because it's travelled the same distance during the first stage and the second stage, if this is 355 metres, then this must be 355 metres. Diagram evidently not to scale. So all I need to find, really, is this value here. And looking back through my question, I'm told at the very beginning it accelerates to a new velocity of 500 metres per second. So I know that this velocity here is 500. So the area of my trapezium is 355, is A plus B, 500 plus 375, over 2 times H. I don't know why I've written that. That should just be delta T. And so delta T is equal to 355 times 2 over 500 plus 375. So I go back to my normal calculator mode. 355 times 2 over 500 plus 375 gives me that my delta T, that's not what I wanted to do, that's what I wanted to do, is equal to 0.811 seconds, and therefore my total time is equal to 1.43 plus 0.811, which is answer plus 1.43, 2.24 seconds. If we look at the mark scheme for that question, for part A you get 1 mark for recognising your integral, so write that down. 1 mark for integrating correctly. As I say, you can probably do that by inspection now, but if you cannot, then substitution is nice and quick. 1 mark for finding C and 1 mark for that being the correct final equation. Part B, evidence of some valid approach to find the time taken. Using the graph is probably the easiest way. Should arguably have sketched that, although just writing your equation was enough here. So you find your value of K, you substitute it into your equation, write down your final answer. As you can see, they've used a slightly different calculator here, but that wouldn't be an issue. And then part C, recognising the velocity of the second stage is linear, so that worked on my graph. And then some valid approach, so either integrating V or just finding the area, this correct equation here, finding your time for stage 2 and adding it to your time for stage 1. And 14 marks of physics masquerading as maths, done.